Before we start, one thing, I got some feedback that last week I was a bit hard to understand, so we cranked up the sensitivity. I hope that works. If not, feel free to interrupt me and tell me to be louder. Okay, and let's get started. Last week we talked a bit about how telescopes work, and we ended on this slightly disappointing result that there are some things that the resolution of your telescope is fundamentally limited by how big a telescope you can build, and that it's not really realistic to build a telescope that's big enough that we can actually resolve a star and see any details of the star. So unless the star is really close, it's basically always going to be just a little dot of light, and that's all we can get from this. So today we're going to talk about another way you can try to understand stars instead, and that's if you just look at basically the color of the star very, very carefully. And just to be a bit clear about what exactly I mean by color is, as we said last week, the light is basically a wave, and that this wave is an oscillation that can swing at different frequencies. And depending on what this frequency is, you can have different kinds of light. So the visible light is kind of in the middle here, and then if you have lower frequencies, you get to infrared light and radio signals. And then if you have higher frequencies, you have ultraviolet light, then X-rays, and then eventually gamma rays. It's probably worth pointing out that there's actually much more to the color than we can see, because the way that our color vision works is that we have, so we have these rod cells that are just there to give us information about if something is light or dark. But then we have three other cells called cone cells that give us this color information. And it's often phrased as, there's one for blue, one for green, and one for red. It's a bit more complicated. So this is a plot here showing the wavelength of the light, and then these lines tell you how sensitive these different cells are for this. So it's not that, for example, we can only see blue light with this kind of cell. So we can see a little bit of green light, for example, and then the other ones are, one is mostly green, one is more reddish, but there's still overlap. But what happens is that if we see a light source, then depending on what color it is, it will stimulate these different cells at different levels, and then our brains interpret this as color. But there's actually more to it, and we kind of have experienced this. If you've ever been somewhere where that's lit by a cheap fluorescent light, you've probably experienced this, that everything feels kind of grim and off and just awful, right? And that is because, so if you look at the sun, how much light is emitted at different frequencies, it's kind of pretty nice. You have something basically everywhere. But if you look at a fluorescent light, it's, you have some very specific frequencies. And especially this kind of red part there's a lot missing. And so if that gets reflected off something, then you may have something that can reflect at, for example, this wavelength. So if there's sunlight, you will get a reflection from this. But if it's fluorescent light, then there's there's no light here for you to see. So then something will look more bluish, and you just very subtly feel that the colors are a little off. And that's kind of weird. It's, we cannot put a finger on it, but it's enough to just kind of make us feel weird. So that's something to be aware of, and also that influences the way that our cameras work. So if you have your camera, then what probably happens is that you have basically these three different types of chips, and one of them is going to be sensitive to red light, one of them is going to be sensitive to green light, and one to blue light. And then if you want to, for example, this projector is going to project some red light, some green light, and some blue light on there, and then it's going to be set up so that our eyes or our brains, I guess, interpret this as these colors. And because the people who built this projector did a good job, it looks pretty much as it would in nature. And doing it this way has some advantages. So one is it works. It's pretty simple. It's easy to understand. If you buy a camera, you probably don't read the manual, if you're honest. And if you go on vacation, you just want to show your friends what it looked like, that's doing a decent job. But there's two problems with that. So one is, you basically need 3 times the pixels, which is not an efficient use of pixels, basically. And the other one is that there's a lot of color, a lot of information getting lost because you're just basically sensitive to just these 3 very specific colors. So in astronomy, what you do instead is you have one CCD chip that's basically sensitive to all wavelengths of light. And then you have, for example, something like this. This is from the James Webb Space Telescopes. For one of the instruments, it is one of 2 color wheels. So there's like these different filters. And then this thing rotates, and you can just push different filters onto your, like in front of your CCD chip. And depending on what filter you do, you can get different colors of light. So this is just for some of these options you have. You can be sensitive to very, very specific frequencies. And then depending on what exactly you want to know, you pick your filters you want to do it, and then you just take one picture after the other. Unfortunately, things in space tend to be fairly, like they don't tend to change on very short time scales. So this is usually a pretty decent way to measure what is emitted in different parts of the spectrum. And so the question is, okay, what can we do with this? So now we know how to measure it. What can we do with it? So if you ever, I guess probably everyone has seen something really hot at some point. So if you imagine you have your iron on the forge, then this part of the iron probably it doesn't emit any visible light, but if you hold your hand against it, you're going to feel it's warm. That's because it's emitting infrared light. Then this part is hotter, so it's orange reddish. Then if it gets hotter and hotter, it gets yellowish and then eventually white. And this guy here, Max Planck, he figured out the way to describe this, or he figured out the way it works. And that's shown here. So this is for different wavelengths, and I've marked the part in the visible spectrum, the part that we can actually see with this rainbow. So everything here is infrared, and everything here is ultraviolet or X-ray. And then up here I marked the color, so the color is steadily increasing, and you can see that everything kind of is shifted to shorter wavelengths. So right, if it's relatively cold, you have basically only infrared. Then if it gets hotter and hotter, you see red light, like you see more and more red light, and eventually blue, and then you can also get ultraviolet and even X-rays. Also, something to notice is the y-axis here. So this is kind of showing you how much light is emitted, and you can see that it's changing very rapidly. So if something gets hotter, it's not only changing the color of the light, it's also the hotter something is, the more light it emits, and this increases very rapidly with temperature. And now the interesting thing is that if we measure the spectrum of a star, it actually looks very close to this spectrum that Max Planck came up with, which makes sense because from our understanding, stars are hot balls of gas, so they should emit something that looks like something hot. So we can measure this, for example, with something called Gaia. Just as an example, this is something you do basically for every star. Gaia has 2 different filters. So one is called B because it's more bluish. One is called R because it's more reddish. And then depending on the temperature of the star, you will see, you will have a different ratio between the red part and the blue part you measure. And from that, you can then calculate the temperature of the star. And based on this, there's a classification for stars that is going through this. So the hottest stars are called O stars, then B, A, F, G, K, M, where M stars are the coldest. If you think this doesn't make any sense, it's because it doesn't. We're gonna get to why it's that. Like, there's a reason for this, but it's not really a good one. And so what you can do now is you can just check. Okay, we take all the stars, or not all the stars, but a lot of the stars we see, and we look at, okay, what's their color and how bright are they? And that's something that was done by these 2 people, Elina Herzsprung and Henry Norris Russell. And so what you get then is this thing called the Herzsprung-Russell diagram. So if a star is, so the x-axis, so the left or right, tells you if a star looks more reddish or more bluish, which also tells you the temperature. So if it's very far to this side, it's a red star, and the further you get to the left, the hotter and the bluer the star gets. And then on the y-axis is the brightness. And this is another weird thing astronomers do. So the further up something is, the star is, the brighter the star is. But if you look at these numbers here, they are kind of decreasing. That's because astronomers use this weird thing to measure brightness called magnitude, where basically if you go from, for example, 1 to 2, then the star is 1/10 as bright. So it's a logarithmic scale, and it's also high numbers mean like a dim star, which is a weird thing to do it, but okay. And now if you do this, you can see there's kind of three regions here. There's the main sequence, which is kind of this line here. And then you see there's a second branch here called the red giant branch. And then there's these stars here that are very, very hot, but also very faint. And so you can see some things here. So first of all, the main sequence stars are by far the most common ones. They're about 90% of the stars we see. And they kind of, they span basically the entire Hertzsprung-Russell diagram, more or less. Then these giant stars are, they're much brighter, but they also tend to be a bit colder, which is kind of weird because we just said that, the hotter something is, the more light it emits. And then the weirdest ones are these stars here, which are very hot, but also very faint. And so the question is, how can we understand this? Well, from the names here, that these are the red giants and these are the white dwarfs, you can probably already guess that it has something to do with their size. It's just because these are smaller, okay. But why are there stars with such different sizes? And in case you were wondering, the sun is about here, so it's a very average main sequence star. So if you want to understand better what's going on there, we need a better way to measure the spectrum of a star. And I guess Pink Floyd was on the right track. If you have a prism and you shine light through it, you get this rainbow color. And this is our guy, Isaac Newton, from last week. He also did some experiments with this. And that's a way you could measure the spectrum of a star. You just shine the light through a prism, and then you have this rainbow, and you can then measure how bright different parts of the rainbow are. And that works, but there's a better way to do it, and you use the fact that light is made of waves. So if you imagine you have your light waves coming here in from the left, and you have two slits here. Then from each of these slits you have another wave kind of radiating out, and you have this refraction that we saw last week. And then the two waves are going to interfere, and it's kind of pretty nice to see in this video with water. Just need to figure out where my mouse cursor is. Hang on. Okay. There. Right. So they're making waves, and you can see that for some directions they're kind of, for example, here they're interfering so that they are canceling each other out. And other places you can see that they're amplifying each other. And we can use this effect because it's going to turn out that this actually depends on the wavelength. So if we, how do I get to the next slide? Okay. So what we do is we build something called a diffraction grating. So we just basically build a wall and put some holes in it, more or less. And then what happens is our light comes in here, and if it goes through one of these slits, it's gonna make all these waves. And then if we have a second slit, for example, here, then it's also gonna have these waves. Now, we want to look at what happens with the waves that go into a certain direction. So let's just pick this direction. So we look at one wave coming from here going this direction, and one wave coming from here going this direction. Now, if they have the correct wavelength, then you can see here that here the maximum of this wave and the maximum of this wave align, and so on. So if we built a screen like somewhere around here, they're gonna amplify each other because you get the maxima together and you get the minima together, and they will add up. Now, if you have another wavelength that's a shorter wavelength, so for example, we take green light, then you can see here there's a maximum here and a minimum here. So if they reach the screen here, they're going to cancel each other out, and we're not going to see any green light here, so we will only see the red light. But what we can do is, well, we just pick a different direction, for example, this one, where the time difference between the arrival times of the wave is different, and now they align again. So here, we have the maximum here and the maximum here aligned, and so on. So in this direction, we're going to have the green light. And if we just kind of do this calculation for every different wavelength, we're going to see that every wavelength is going to get deflected effectively to a different direction. And so we just basically then put a CCD sensor here, and now we can measure the spectrum very precisely. And this would work perfectly well. There's only one problem, and that is actually, most of the light is stopped at this wall. And if we were looking for a very faint star, that's kind of a bummer. So what we do instead, we build something called a reflection grating, which is basically a mirror that's set up, that's split up in all these different little triangles. And if you look at light, for example, like coming from this direction, then there's going to be some time difference between the light being reflected from, for example, this surface here and this surface. And you still have, the same effect that for different directions, the time difference between the waves is going to be different, and so you have different wavelengths, amplified and different wavelengths canceling each other out. And you can do this, but now you have a different problem, and that is we kind of saw something like this last week, and I called it, or it is called chromatic aberration because it makes your picture blurry. So last week we put all this effort into getting a nice crisp picture, and now we're just destroying it. So, now if we did this for like our entire telescope picture, then we just get like some mushy thing that we can't really do anything with. So what you can do instead is you do something called slit spectroscopy. And that is you put a very thin slit in front of your sensor that will only that only lets through a little slit of light. And then you set up your diffraction grating so that this splitting up into the different colors, that goes into this direction. Right? So you not only see a very small part of your picture, but for every little part of that picture, you can just, you know very well where it goes. So as long as everything you want to see is on a line, that's very convenient. You can now do very precise spectroscopy. And this is just one example. So this is something called a reflective nebula, which is basically a gas cloud. And there's a very hot star here that's getting reflected off the gas cloud. And so this is what the picture actually looks like. And then if you put in the diffraction grating, you get this. So now you have basically how far along this slit here you are, and then this is basically how much light is emitted at what wavelength. And now we can, and as I said, this works very well if everything you want to see is on a line. If it's not, you just have to kind of move your line somewhere, take a picture, move your line somewhere else, take another picture, and so on. That can take a long time. But there's different ways you can do it, or there's alternatives. So, for example, the James Webb Space Telescope has something called a shutter array. It's kind of pretty small. It's kind of like a little chip. And it has, hang on, I noted this down. So it has 249,660 little windows that look like this. It has a little magnetic arm that kind of goes over the this array of pixels, and it can open each one of these individually. So now you basically still kind of have a slit, but you can, you can basically have the slits at different places. And what you can also have is if you can have two slits, and if they're far away from each other, then the spectra won't overlap, and you can still see more objects. And this is just an example of what that looks like for a test image. So they have a little calibration source in there to just where they know how bright it is, what its spectrum is. And if you look at this through the spectrograph, you can see here this, all these spectra are at different some are further left, some are further right. But if you imagine there's a bunch of stars here, for example, you can now take take pictures of a bunch of stars at the same time.
Each of these horizontal lines is a spectrum?
Yes. So for example here, this is one spectrum, this is one spectrum, and then everything, like each line here is also a spectrum. So you can take, however many objects you're interested in there. Well, there's some limit. And you can go even further with this, and just basically you take your entire picture and make it a line. So this is something called the dark energy spectroscopy instrument, and its job is to just take the spectra of as many distant galaxies as it can. And so what it does is it has these optical fibers. So these are, your fiber optic cable is basically the same thing that you have at home. And what you do is you just basically have your telescope send the light into all these fibers, and then you can just send each of these fibers into a different spectrograph. So now you basically, like each of your pixels, more or less, you can take a spectrum of. And that allows you to just, take many, many spectra all at the same time. Okay, so now we can take very precise spectra, but what do we do with this? So the first people who kind of looked at this were Josef von Fraunhofer, who usually gets the credit for this, but there was also another guy, William Wollaston, who also found this, but he kind of didn't really publish it and was kind of forgotten, but just to give credit where credit is due. So they looked at the spectrum of the sun, and they noticed that, it has this rainbow, but then in this rainbow, there are all these little lines here. And back then they couldn't see all of them because their instrument was not good enough, but today with modern spectrographs, we can see hundreds of lines in here. And so the question is, well, where do they come from? And for that, let's go back to our fluorescent light, where we just said it has this really unpleasant spectrum. Well, why does it look like this? Why does our fluorescent light bulb only emit at certain frequencies? And for that, we have to now kind of go back to Earth and look at how exactly an atom works. So if we start with just the simplest atom, which is hydrogen, what you have there is you have a proton in the middle, and then you have a little electron kind of on the outside. And usually this electron is in something called the ground state, which means it has a certain energy, it has a certain momentum, and so on. But there are other states it can have, and this often gets drawn as this kind of like orbital system, which is not quite correct. It's a lot more complicated than this, but what we need to know now is basically that this electron can be in different what's called states, and then it will have a different energy. So it can be in these are named with a number called n. So it can be in the n equals 1 state, which is kind of the lowest energy state, or it can get more energy if it goes to the n equals 2 state, and so on. And there's this slightly weird convention that the energies here are negative. So the energy is proportional to 1 divided by n squared. Yes?
How many energy levels are there in the hydrogen atom before, if you strike it with a photon, it's just going to go flying off?
It's kind of hard to tell because in theory, I think it's basically infinitely many. At some point, the question is can you really actually measure these states? But it's hundreds in principle. But really, actually relevant, we're going to get to get there. Actually relevant are only a handful in this part. But in theory, you can have a lot. Yeah. So there's this slightly weird convention where the energy is negative, and the idea is that if you have you have 1 proton and you have 1 electron, and they're basically very, very far apart, then you say that energy is 0. And then if the electron gets captured by this proton, then it's going to emit energy, and so you end up with negative energy. But the important part here is basically that depending on this electron can have different energy states. And now, these are the energy states. And just to mention it, I don't want to make it too complicated. Actually, even within these states, there are finer structures. So they're actually kind of like substates, which very, very similar energy levels, but they are very slightly different. And now what can happen is you have a gas. If the gas is hot, or even if it's relatively cold, your atoms are going to bump into each other. And what can happen then is that your electron goes from a low energy state to a higher energy state. And most of the time, it's not going to stay there long, and it's going to go down to the ground state. Yes?
Did anybody explain how energy is communicated to the electron moving up and down? How? Explain it.
Basically, through a photon. It's complicated. It's basically like a whole other lecture's worth of theory behind that. But it's basically through a photon.
It's a photon, but
Yes.
how does the photon gives its energy to the electron?
Essentially it will travel between, for example, the proton and the electron. There's a bit more to it, but it's pretty well understood. Yes. Okay. So if our electron now goes back to the ground state, it will emit some light. And our friend Max Planck from earlier has figured out that the energy or the wavelength of this light will depend on the difference in energy between the two states that the electron traveled between. And this is basically, or in essence, how fluorescent light works. You have, in this case, mercury. You electrocute it. You excite these electrons to go up to the state, to a higher energy state. And from there, they're going to go back down and emit light. And then there's a little bit more technical details to it, but that's kind of the very fundamental principle. So if the electron goes from a lower, from a not quite as high energy state to the ground state, it's going to emit a longer wavelength photon. And now the interesting thing is that this process can also go the other way around. So if you shine light at an atom, it can also absorb this light, and then the electron goes from, for example, the ground state to another state. But the probability it is most likely to do this if the wavelength of the light is the same or very close to the wavelength of the light that it would emit if it went the other way. So now we can kind of understand where these lines come from, because you have the star producing light somewhere in the interior, and then you have kind of an atmosphere called the photosphere full of light, and then if the light emitted is at a frequency that corresponds to the difference in one of these, or in two of these different energy states, then it's more likely to be absorbed. And it's going to be emitted, but it's not necessarily going to be emitted in the same direction. Right? It might just be emitted back into the star. And so this line gets weaker. And now you can basically look, you take all the elements you look at, okay, what light do they absorb? And then you compare those to the sun, and you can see, you can match certain lines to certain elements. And so if we do this for the sun, it looks something like this. So first of all, you see oxygen that is not actually from the sun, it's from the atmosphere. That's what this telluric O2 means, and also this water vapor. But the other stuff, for example, we see iron here, we see sodium, we see a lot of hydrogen, we see some helium. And from this, we can kind of understand what we now know that these elements have to be there. And there was an interesting thing that happened, and that is there's this little line that's fairly small, and these two people, Per-Jules Jensen and Joseph Lockyer, they saw this line, and actually, to be perfectly honest, they didn't see the absorption line they saw during an eclipse. They saw the emission line, because during an eclipse, what happens is, most of the sun is blocked, so you can really only see this light that is absorbed by these atoms in the outer atmosphere and then emitted. So then you actually see these lines as emission lines, where the light is brighter. But they saw a line there that didn't match any element that anyone knew at the time. And so they figured, okay, there must be some element here that we haven't discovered yet. And if you know some Greek, you can probably guess what it is. It's this one, helium. Helios is Greek for the sun, so that's why it's called helium. And then eventually it was also discovered on Earth, but it was actually first discovered, interestingly, on the sun. But there's kind of a weird thing is, why is this line so weak? Because to just do some foreshadowing, we know there's a lot of helium in the sun. And we also know that most of the rest of the sun is hydrogen. But if you look at these, for example, these hydrogen lines, they're pretty strong. But for example, take these iron lines here, they are almost as strong. There's a lot less iron in the sun than hydrogen and helium. And that's because actually these hydrogen lines are not from this process where you have the ground state and then that gets excited. It's actually already in an excited state and then goes to an even higher state. Because if this happens, this line is actually in the ultraviolet and you cannot see it with your eyes. And this kind of brings us to a different thing, and that is actually which lines you see and which you don't also depends on the temperature of the star. Because if you imagine that there are no hydrogen atoms where you have any hydrogen in this excited state, then of course you don't, this line cannot happen. So you need enough hydrogen atoms in the state for them to be there to absorb it. So what needs to happen a lot is that hydrogen atoms collide, and this collision then causes this excited state, and then light comes by just at the right time to be absorbed. And for that, you need a certain temperature. And so this is for our our star classifications from earlier. So this is the hottest stars are up here, and then the coldest stars are here. And this is if we assume they are made up of the exact same material, this is what lines you would see. And so the reason why earlier these spectral classes didn't make sense is because I've been kind of telling the story backwards. This is actually where these classifications come from. People were just looking at these lines and seeing some patterns. And back then it was actually A, B, C, D, E, and so on. But then eventually people figured out that it actually basically depends on the temperature, and they figured out that some of these classes are redundant. So that's where, for example, there's no D class, and that they are in the wrong order. So that's why these letters are in this weird order. But so if you kind of start at the coldest stars, you can see, for example, you can see Titan oxide, so you can actually see molecules here, because a star is cold enough that these can form there. Then if your star gets hotter, these atoms here are being ripped apart, and then you can see, or you cannot see these lines anymore. And so because of this, if you go from an M star to a K star, you don't see molecules anymore. You see these kind of neutral atoms. If you then with a G star, you see, where is it? You can start seeing these hydrogen lines, because now you have these excited hydrogen states that allow you to emit these or that allow you to absorb these frequencies of light. So that's why you can see these hydrogen lines appearing, and then eventually you see them disappear. And that is because the star is getting so hot that your atoms are colliding with such energy that the electron just gets kicked out completely. And then suddenly you don't have an electron anymore to do this absorption. And what you can also see is, for example, helium. Where is it? So you have what's called helium-1, which is helium that has lost one of its electrons. So helium has 2 electrons in its shell. And if it loses one of the electrons, you can see this in these absorption lines. And see that, for the cold stars, you see basically no helium or no ionized helium. Then you see it, and then eventually you don't see it anymore because it's getting so hot that it's lost both of its electrons. Okay, now what you can do is you need to do some modeling. So what you can do is you say, okay, I know the temperature of the star or of the star's atmosphere from kind of the overall spectrum, right? And what I can do is I can now model its atmosphere and model what elements are in there, and I can calculate, okay, what spectrum do I expect to see, and then I compare that to what I actually see, and then I can measure what elements are there in the star. And if I do this, it looks like this. So this is the solar system composition, but the solar system is like 99.9 something percent the sun, so close enough. And you probably know this periodic table. So if you basically go one line from left to right after the other, you basically always add one proton, which is called the atomic number, which is plotted on the x-axis here. And then on the y-axis is how common this is. And this is a logarithmic scale, so from 1 to here, for example, an element that's here is 10, or an element that's up here is 10 times as common as something that's here, for example. So there are much, much bigger differences in these abundances. And if we look at this, we see some pretty interesting patterns. So first of all, we see helium and especially hydrogen are much, much more common than basically anything else. We also see that then the next three elements that are just slightly heavier than hydrogen are some of the least common elements overall. But then suddenly again, carbon and oxygen are again super abundant, and also iron for some reason. It's not the most abundant, but you have this kind of weird peak here, right, where suddenly your abundance increases. And of course, you also see this kind of weird zigzag pattern, right? You have a common element, a less common, common, less common, common, and so on, right? The question is, why is it like this? Can we explain this? And another thing we can do is because hydrogen and helium are so much more common than anything else, a lot of the time astronomers use a different periodic table that looks like this, where basically everything is either helium or hydrogen or just something called a metal, which, yes, most of them chemists would say are not metals, but that's what astronomers say. And we can just measure how much stuff is in a star that is not hydrogen and not helium. And this number is called the metallicity. So we can have very metallic stars if there's a lot of heavier elements than helium in there. And if you do this to a bunch of stars, you see an interesting pattern, and that is you see kind of two different populations of stars called population 1 stars and population 2 stars. So this is this is what the spectrum of the sun looks like. So you have a lot of absorption lines. And our sun is something called a population 1 star, where you have a fairly large amount of metals in there. And then you have something called population 2 stars, where you basically almost see only hydrogen lines. This is extreme examples. So this is from the European Southern Observatory. These are like the two most metal-poor stars that have ever been discovered. So a lot of the time you see like a little bit of absorption lines, but you can see stars that have basically no metals. Or these are that have very, very few metals. And in theory, people expect to also see stars that have basically absolutely no metals at all, that are purely hydrogen and helium. No one has found any of these yet, because they probably died billions of years ago. Okay, so now we looked at our stars and we found some interesting patterns that we want to explain. So first of all, why are there these three different categories of stars? Why do we have the main sequence, and then we have these giants and these dwarfs? And why are the main sequence stars so much more common? And why do we see more carbon, oxygen, and iron than most of the other metals? And why is there this weird zigzag pattern in the abundances, where you have a common metal, a less common metal, common metal, less common metal. And then why are there these two populations of stars? And another thing about these is that the population 2 stars, so the stars that have very few metals, tend to be colder. And they are also more in kind of like far away from the center of the galaxy, whereas the population 1 stars, where you have a lot of metals, tend to be closer to the center, in the spiral arms and also kind of the inner parts of the galaxy. And now we just ask our theory friends, okay, how do you think a star works? And what they will tell you is that there is a core in the middle where the energy is generated, and then you have outer layers of gas, basically, and these are split into different zones that we don't need to get into. But what happens in the middle is nuclear fusion, where you have basically hydrogen atoms combining and forming helium, and this is something, for better or worse, we figured out how to do on Earth. So this is something we understand pretty well, and we can model. And so if we ask nuclear physicists, okay, what needs to be going on here? Well, first, what needs to happen is you have 2 hydrogen atoms or 2 hydrogen nuclei combining, and then one of them turns into a neutron, and what you have then is called deuterium, which is just basically you have 1 proton and one neutron together. Now, the problem with this is that last week we talked about how if you have 2 charges that have like 2 equal charges, they will repel each other. So for them to get kind of close enough to actually be able to start this fusion, they need to be very hot, because then the gas moves faster, and then you can kind of smash them together hard enough that they can actually do this fusion. And then if you have this, then your deuterium can absorb another hydrogen nucleus, and then you get helium, something called helium-3, where you have 3 particles together. And then 2 of those can combine, and they will kind of decay into helium-4, which is a very stable nucleus, and then it will also kind of release 2 protons again. Now, this is one way a star can make energy, but people try to model it, and for some stars, like this mechanism alone could not account for all the energy that was being generated. And the reason for that is that this process here, where you have 2 hydrogen atoms together forming deuterium, that is very inefficient because it involves something called the weak nuclear force, which from the name you can tell is weak. So the likelihood for this happening is pretty small. But there's another process. Another process that can explain this, that you can model. That is something called the CNO cycle, because it involves carbon, nitrogen, and oxygen. And basically what happens is you can use carbon, nitrogen, and oxygen as a catalyst. So basically what happens is you have a carbon absorbing a proton, which turns into nitrogen. Then that decays into carbon again, which produces another proton. You have nitrogen again, and so on. So you have this chain of a heavy nucleus absorbing a proton, decaying, and then absorbing another one. But eventually what will happen is that you have nitrogen absorbing another hydrogen atom and emitting helium. And then you end up with the same carbon nucleus that you started with. So the carbon doesn't actually it's like a chemical catalyst. The carbon doesn't actually get used up, but it just facilitates this this reaction. Now, the problem with this is, as I said earlier, your gas needs to be hot to overcome this repulsion, and now you have carbon involved, which has I forgot how, I think 6 protons, so it has 6 times the repulsive force. So to overcome that, you need even more heat than for hydrogen for this process.
Was this produced on Earth in some laboratory?
I don't think there's any There's definitely like no large-scale use of this because it's kind of complicated.
So it is only theory?
Yes, but you can measure these processes individually very easily. You can just take your carbon nucleus and shoot a hydrogen atom at it.
But this is just by mind. It's really never happened in laboratory.
Well, you can do these processes in a laboratory. You just take your
You can?
yeah. You just take your carbon or whatever and shoot a shoot a proton at it, and you see what happens. You can do this in the lab. You just don't get this whole cycle because it tends to be at colder temperatures. But you can measure this in the lab, yes. And now this is how you get helium. Then the next stage is using this helium up again. And again, you can ask your nuclear physicists how this should work. And what happens there is you can have your two helium nucleuses form beryllium. But this form of beryllium is actually very unstable. It will decay pretty quickly. But if you're lucky, what will happen is another helium nucleus will collide with it and also get absorbed, and then you get carbon. But the thing is, because for this you need because to overcome the repulsion of your helium nuclei, and because it has to happen quickly, because you need this step to happen before your beryllium decays. You need even more. You need an even hotter star. And so what you can do is you model, okay, how does the efficiency of these processes depend on the temperature of the star? And you see that for a fairly colder star, this cold star, this first process, called the PP chain, is the most efficient one. But if it gets hot enough, you have this second CNO cycle. And if it gets even hotter, you can fuse helium, which emits even more energy. And so that means a hot star has a much more efficient energy generation, and it also this also means that it will also burn up its fuel much quicker. So our sun is kind of here where you have like a little bit of this carbon of the CNO cycle happening, but this makes up like 1% of energy production. Most of it is this very inefficient process, which is good for us because that means the sun will last much longer. It will last like 10 billion years. Now, another interesting thing is that what you can also measure is like how much energy gets generated if you fuse to certain nuclei. And what you can see here is that iron is kind of the most stable nucleus. So if you try to fuse iron with anything else, it will cost energy. And that's why there's so much iron, because basically any fusion chain has to more or less end at iron, because this is, you cannot generate energy after this. Okay. Am I forgetting something? Oh yeah, one other thing to notice. With this process here, we basically, we started with helium, and now we're at carbon. So we just skipped a bunch of elements. We skipped those 3 elements that we saw earlier, were so very rare. And this is why, because this fusion chain basically skips past them, and there's no really efficient ways to generate these in a star. It also explains why you see this zigzag pattern, because you just always end up combining kind of 2 protons together. So if you have something that has an even number of protons in its nucleus, it is much easier to produce through just putting a bunch of helium together than getting something that has an odd number. So that explains that feature. And another interesting thing is, so I said earlier that our sun only does this PP chain burning, so it actually can only generate helium. So why is there iron and calcium and all that stuff in the sun? It cannot be produced there. Cannot be produced there right now. And what that means is it has to come from somewhere else. So these heavier metals, or basically any metals in the sun, cannot be produced by the sun right now. They have to have been produced by other stars earlier. And now, okay, so this means if you have a very old star, then you don't actually expect a lot of metals in there, right? Because there were fewer stars before them to produce these heavy elements. And that explains why there are these two populations. It also explains why these metal poor stars are much colder, because if they were hot, then they could do this efficient fusion here, so they would not live as long. So yeah, there were probably hot population 2 stars at some point, but all the very efficient ones have already basically died long ago. So basically, we only see these cold population 2 stars because they're kind of the last ones left. So if we go back to our questions, so why are there these different stars? Well, that's because probably the giant stars started one of these more efficient production channels. And so that allows them to generate more energy, and that's why they tend to be brighter. Okay, why are the main sequence stars so much more common? Because, well, if the giant stars do these more efficient fusion processes, they cannot live as long, so they die quicker, so there's fewer of them there at any point, right? Why are carbon, oxygen, and iron so common in stars? Is because there are efficient processes to produce them compared to other elements. And that's also why there's these even and odd numbered, there's the difference with these even and odd numbered elements. And yeah, the population 1 and 2 stars are different, basically because the population 2 stars are older, and that means they have to be colder to survive long enough for us to still be able to see them. And it also explains why there are more population 1 stars with more metals in the spiral arms, because if you model kind of how stars form, we expect the spiral arms, because they are much denser, to basically generate much, much more young stars. So now if we just basically look at how we think these fusion processes work, we can suddenly explain all these observations we just made. Except, what about the white dwarfs? Can we tell something about them? So, they're down here. So, first of all, if they are so hot, why are they so weak? Or why are they so faint? Well, there is something called the Stefan Boltzmann law, which kind of tells you how much basically a warm object or a hot object should emit, and it kind of depends on the temperature, some constant that is just it's a number we can measure, and then it's the area of that object. So if they don't emit a lot of light, that means they have to be very small, so they have a small area, right? And we can calculate, okay, from what temperature they have, we can calculate, okay, how big would they have to be to emit, this little light. And it turns out they would actually have to be something like the size of the Earth, so they have to be really, really small. Now, the next thing we can do is, there's a lot of the time you have these white dwarfs in what's called a binary system. So this is a star called Sirius A, which is one of the closest stars to Earth. It's actually the brightest star, or the star that appears brightest to us. And if you look here, there's a little thingy next to it, and that's a white dwarf. And it's kind of called the pup, because the stars in the constellation, the big dog, Canis Major, which is kind of cute. Now, in this case, we can actually just see it, but a lot of the time, because the star is so far away, or they're so far away, they're going to be so close to each other that we cannot resolve them. But we can actually use spectroscopy for that to see them anyway, and that we use something called the Doppler effect, which is something you probably know from everyday life. If if there's an ambulance going past you, it makes this wheew, yeah. And that's because when something moves towards you, the sound waves will kind of be crunched together, so you hear a higher frequency. And if it's moving away from you, they're going to be spaced further apart, so it's going to be kind of like what's called a lower tone. And the same thing happens with light. And the nice thing about these spectral lines is that they are from elements we know. And this Doppler effect, it will change where these lines are, but it will not change the distance between them. So if we know that two lines have to be a certain distance from each other, we can look for two lines that are in that distance, and then we can measure how much they are shifted either to the blue or to the red, and from that we can calculate how quickly that object or that star is moving. And now if you have this a binary system, then these stars are kind of circle around each other, right? So at some point during this, they're going to basically, one of them is going to move to the left, one of them is going to move to the right. So none of them are going to move basically towards us, right? So in that case, the spectral lines are going to look the same. But if one of them is moving away and one of them is moving towards us, then one of them has the spectral lines shifted one way and one the other way. So now suddenly, you see this doubling in the spectral lines. Then later, again, they're not moving towards us. You see them come together. And then, again, they're moving apart, but this time the other way around. So if, one star has stronger spectral lines than the other one, you can actually tell that, now they're moving kind of the opposite way. And from this, we can kind of model how their orbits are. And from this, we can measure we can measure the mass of these stars, because we know that this has to be due to gravity, and we can calculate, okay, how strongly do they have to attract each other for the orbits to look like this, and from that we can calculate how heavy are they. And if we do this for white dwarf, for example, for this Sirius B, as I said earlier, it's probably roughly the size of Earth, but the mass is roughly the mass of the Sun, which is about 330,000 times as heavy as the Earth. So this object has to be incredibly dense. And what we believe it is it used to be the core of a star, but then that star exploded, the outer parts were kind of ripped apart, and what's left is this extremely dense core. And we can actually see this in some pictures. So there's a white dwarf here, and you can kind of see the rest of the star has been exploded a long time ago. But we're going to talk a bit more about white dwarfs next week, because it turns out they're actually very important if you want to know how far away a galaxy is. So I see you then. Okay, I see a lot of questions.
Can you go back to your Russell-Hartström diagram?
Yes. Let's take this.
In terms of variable stars, is there a particular group that they appear to hang around in or occur more frequently in, as opposed to somewhere like main sequence?
I was going to talk about that next week, but okay. Okay, it depends on what binaries you're talking about. So there's, for example, there's called, what's it called? There's binary variables. I forgot the term. But what can happen in this situation is that you have one star moving in front of the other and blocking it. That can be a variable, or look like a variable star to you, or to us on Earth. I mean, those can be anywhere on the Hertzsprung-Russell diagram. The ones you're probably thinking about are delta Cepheids, which are a very important class of variable star, and they tend to be around, like, kind of here, I think. So there are certain classes of variable star that you will see at a very particular point in there. Actually, you're not going to see them at one point because they're variable, so they're kind of moving up and down here. But yeah, some of them you will see there. Yeah.
They always say in these astronomy specials that they have in nova and so on. We don't fully understand what's going on in the center of the star. What's the main problem? They don't understand fusion. They understand all kinds of stuff. What's the main problem?
Okay, I mean, a big problem is that fluid dynamics is very hard. And it's even worse in stars because for some of them, or probably most of them, also magnetic fields are going to be important. So you have to do what's called magnetohydrodynamics, which is already fluid dynamics itself is already pretty difficult, but then you have to involve magnetic fields. And that's just very hard to model. So that's probably the biggest thing right now. Yeah, I guess the fluid dynamics is probably the hardest part. Yeah?
Your diagram where the photons are exiting from the star or from a hot body, okay? looks, once they release the star, they go at speed of light. And how about just before that, when they are in the star? What speed they are?
Well, so it's okay. So I mean, they are. You mean here, right? It's like if they're somewhere here, for example. So they're, in principle, they're going at the speed of light.
Inside?
In principle, yes, but because this is very, like this is pretty dense and stars are big, they're going to get scattered a lot. So they're, like in here, it can actually take it does take probably a long time for the light to go from the center of the star to the outside. But that's not because it's moving slower, it's just because it's getting scattered a lot. Yeah.
So with the James Webb, can we see far enough back in time that we can see those populations of stars that are less common now?
Yes, I think so. I mean, so the problem is that it's very difficult to see individual stars in very distant galaxies. There are some times where you can get very, very lucky, and because there's certain. It has to do with gravitational lensing. You can just have like gravitational lens like just at the right spot that it's amplifying a star. Then you can do it, but it's you can kind of see the average spectrum of a bunch of stars in the galaxy. That kind of works. And I would have to look it up if they can actually confirm that there's more distance, that the distant stars are a different population. I would have to look that up. I'm not sure.
Thank you.
Yeah, back there.
When you're observing a distant star spectrum and analyzing it, do you have to worry about the interstellar dust?
Oh, yes. You're all talking about stuff that I want to talk about next week. Yes. So what happens is it's actually kind of the same thing with like why the sky is blue and why the sunsets are red, because the short wavelength light tends to get scattered more on dust, and you can kind of see this. So stars where there's a lot of dust in the middle tend to look redder because they tend to scatter the blue light more, which is actually also useful because we know what the spectrum should look like. So if it looks different, if it looks more red than it should based on the temperature, we can measure how much dust there has to be in the way. And that's actually extremely important for a bunch of stuff because the dust can do all kinds of stuff doing measurements. But yes. Yeah?
So last week you had a video where you had a series of oscillators on the left generating waves, and as they propagated there were interferences until by the time they got to the right there was a rather regular series of flat plane waves propagating beyond that. And most of what I recall the first lecture had to do with interferences and wave kind of physics, and electromagnetic waves in particular. Yet, on the other hand, if I recall, when the Hubble deep field photo was first published, there was something about it was a ridiculously low frequency of photons being measured. I can't remember what it was, like maybe every 2 or 3 seconds you get one photon.
Yeah.
And I know that in Super Kamiokande with Neutrino Observatory, you're dealing with one neutrino at a time. Can you say something about, are you dealing mostly with waves in Maxwell's theory in your telemetry, your various observations? Can you say something about the relationship of that to things that involve quantum mechanics, specifically discrete events?
Yeah. Okay. Okay. How do you explain quantum mechanics in 5 minutes? Okay. So if we take our grating here. Something you can actually do is you can, for example, you can have a very, very faint laser, for example, and shoot one photon at a time through there. what will happen is you will still see these diffraction patterns there, because quantum mechanics, like one of the way I like to call it is particles will act as waves or as particles depending on what questions you ask. So if it's about propagation, like this situation, they act like waves. And you can also do the same with, for example, electrons. That also works. They will also do this diffraction pattern. But if you're kind of asking where precisely is this photon or this electron or whatever, so if it, for example, you wanted to interact with your CCD, like a certain pixel of your CCD chip, then it will always have to pick a certain position. So then you will always see like one interaction. It will act like a particle where either you see an interaction or you don't. Now, an interesting thing with light is that, for example, for radio waves, because they have such long wavelength, you basically you're not able to measure like a single photon at radio frequencies. So you will always have to, your antenna will always have to interact with, I don't know how many photons at the same time. So with that, you will always basically see the wave character. I hope that answers the question. I don't know how good a job I did.
So when you send a photon through there and it does split into smaller photons or what?
Well, it's okay. That's kind of I think a general thing with physics is we can describe how, like, what it's doing. If you want like a picture in your head and you want it to kind of intuitively make sense, I don't think you're going to get that from quantum mechanics. So it's like
once it passes to the other side, it is spread into two waves.
Okay, so
does that mean it split into two pieces?
Well, so that's an interesting thing. So what you could do is you could say, okay, I want to know which one of these slits it went through, right? So you build a detector on each of them, and you measure, okay, does it pass through this slit or through that? Now what happens then is you will always only you will only see it in one of the slits. But what also will happen if you make this measurement is that the diffraction pattern here will disappear. It's weird, yes.
Is it possible that it may be not wave and particle at the same time? It is at different time?
I mean, the thing is, if you just take quantum mechanics for what it is, then this behavior is exactly what you would expect. The problem, we have this is nice phrase, or I guess not nice, saying in quantum mechanics, shut up and calculate. It's like a lot of the time you just have to do the math, unfortunately, which is complicated. But if you just take the equations we have as they are, and you calculate, okay, what should my photon, my electron, or whatever I want to send through these slits, what should it do? It should do exactly what it does. I unfortunately really also don't have a really intuitive way to think about quantum mechanics that really works all the way down. It's somewhat unsatisfying, but the equations work, at least. Yeah?
What are you going to talk about next week?
How we measure distances. Distances. How do we measure how far away a star is, or a galaxy, or whatever? Yeah?
Are we any closer to figuring out how big a star can get, thinking like VOI, Canis Majoris, and bigger ones even than that, or a billion times bigger than the sun and so on. Large, I mean. So do we know a limit, or?
I don't know if there's a theoretical limit.
Pardon?
I don't know if there's like a theoretical limit. I mean, there's probably something, right? If you make stuff infinitely big, at some point, something's going to happen, right? Like, there's probably some limit. I don't know what it is, to be honest.
Okay.
Yeah?
Yeah, since you mentioned the star Sirius and its companion, do you have any opinion about the legend of the Dogon people in Africa that supposedly knew about the companion star before astronomers did?
I remember read. I
It's
remember.
a thing amongst UFO enthusiasts, of course.
I vaguely remember reading about this like 10 years ago. So I
It was known back in the 50s, I think.
I mean, so there is, okay. There are claims that you can, like, that some people can see Sirius B by eye.
Uh-huh.
I think for that you would have to ask a psychologist if you know there is a star. I don't know. If you would,
Is
I
it
don't
on the verge of visibility? Maybe it is.
yes, it's. I mean, it is close enough
Some
that.
people might have seen Uranus before.
Yeah, I mean, it is close enough that people don't automatically disregard claims that by people who say they can see it by eye. So it might be possible, but
Fair enough.
I don't remember like the details about this. Okay, yeah, back there.
Are there any cases of photons scattering photons?
Yes, and we're going to talk about this in 5 weeks? 4 weeks. Yes, if you have extremely short wave light, then they can scatter each other, which is actually a problem for if you want to see very, very high energy light.
So you're saying that high energy photons will bounce off of each other? They won't go through each other?
Well, what will happen is they will produce an electron and a positron, which is the antiparticle to the electron. They will basically produce new particles. That's the interaction they can do.
All by themselves? There's no mass nearby when they collide?
Yeah, it's by themselves.
Pardon?
It's by themselves, if they have enough energy. Okay, yeah.
White dwarfs have high density. What does this tell us about their gravity and then their relationship with the other objects in their neighborhood?
Okay, another cool thing you can do with this redshift is you can also measure how the gravitational pull at the surface of the white dwarf, because according to general relativity, if you have kind of something has to get out of, like, if light has to get away from something that has a very strong gravitational pull, then it will also redshift. And you can measure this. And this is actually a way you can confirm that actually our estimates of the size and the mass are actually roughly correct. So you can measure this gravitational pull. We're also going to talk about that next week. You can actually have a white dwarf kind of strip away gas from its companion star. That is something that happens. And yeah, we're going to talk about this next week. Okay, I don't see more questions, and yeah, see you next week.